So hello everyone, our today's topic is the casting defect. So first of all, you should know what is casting. So casting, it is a process in which molten material, typically metal or plastic, it is poured into a mold cavity to create a solid object of the desired shape. So once the material it get cools and solidify, it take the shape and form of the mold, resulting in the finished products. The dental casting, on the other hand, is the defects. It is the defect or discrepancy that occurs during the step followed through the impression making, pouring, cast, and fabrication of wax pattern to investing and casting procedure. So distortion. So the dental casting, it is a form of defect that can impact the quality of the final dental restoration. Now let us discuss the various classification of the casting defect. According to the Phillips, the classification can be based on the following. There can be distortion, surface roughness, irregularities, discoloration, formation of air bubbles, water films, rapid heating, underheating, inadequate water-liquid ratio, prolonged heating, temperature of the alloy, or due to the casting pressure, composition of investing materials, foreign bodies, all those that can result or lead to these defects. There could be porosity like solidification defect or localized shrinkage porosity that we shall be discussing later on. Microporosity, porosity due to trapped gases like pinhole porosity, gas inclusions, subsurface porosity, or the residual air. So we shall be discussing all them one by one. This classification is according to O'Brien. The problems with the external porosity like back surface porosity, problems with internal porosity, localized shrinkage porosity, subsurface porosity, microporosity. So let us discuss them one by one. According to the Rosenstiel, the classification that could be roughness, nodules, fins, voids. So let us discuss them one by one. The first casting defect is the distortion. So distortion is a defect that can affect both the wax pattern and the resulting casting. So any marked distortion of the casting, it is related to the distortion of the wax pattern. So the wax temperature is very crucial. So the temperature at which wax pattern it is manipulated is crucial. If the wax it is too cold, it can. So if the wax it is too cold, the pattern undergoes stress release with the change in the shape. And if the wax is too hot, excessive shrinkage could result on the cooling. So if the wax is too hot, it can become soft and deform easily. So the wax pattern, they need time to cool and set properly after the shaping. So if the wax is disturbed before it has fully set, it can lead to distortion. So proper cooling and setting time, they are essential to avoid this tissue. The third is the hygroscopic expansion. So this the investment material used in a dental casting is designed to absorb water. It will absorb water. So during the investment process, this investment material, it begins to expand. As it absorbs water. So if the expansion it is not uniform or controlled, that could lead to distortion in the wax pattern trapped within it. Now, what would be the effect of distortion? There would be fit issues. There can be distortion can affect the appearance of final restoration. There could be functional problems. So, to prevent the distortion and other casting defect, so one has to ensure that the wax it is at correct temperature. So one should allow sufficient cooling and setting time of the wax. Or one should use high quality investment materials. Follow proper investment techniques to control the expansion. So the wax distortion, how it can be minimized? The first is manipulation of wax at high temperature. Second, investing the pattern within 1 hour after finishing. And if storage is required, one should store it in refrigerator. The next is the surface discoloration. The surface discoloration of the dental castings, such as those made from the precious metals like gold, silver, can be due to the various factors. So one of the main cause is the sulfur contamination. The sulfur contamination, it can come from various sources like the atmosphere or the materials used in the casting procedure. So the sulfur contamination of the casting can cause black castings. There can be contamination with copper during pickling procedures. So what you have to do is avoid overheating. So remember, overheating during the casting procedure, it will lead to release of sulfur compounds. So these compounds can react with the metal surface that can cause discoloration. So the proper temperature control is essential to prevent overheating. Other is avoid the use of steel tongue to hold the casting during pickling. So using a steel tongue to hold the casting during pickling, that is a process that removes the oxide from the contaminant. That is pickling. It removes the oxide. So that can introduce iron into the solution. So this iron can react with the metal surface and therefore cause surface discoloration. Other is to avoid placing casting near the amalgam dies or scrap. So amalgam, a dental material containing mercury and other metals, it can release vapors that may react with the casting surface and that may cause discoloration. So to prevent this, it is important to keep the dental casting away from the amalgam related products. ensure complete elimination of the wax pattern during the mold heating, as the incomplete removal that can lead to carbonized wax on the casting, so that can cause black casting. So this residue, it can be removed by heating over the flame. So the type of flame used in the casting procedure, it matters. Oxidizing flame, that will have more of oxygen, so that can cause surface oxidation and discoloration of casting. So instead oxidizing flame, one should use a reducing flame that is fuel rich and helps to prevent this issue. The other cause is the surface roughness or irregularities. So the surface of dental casting should be accurate reproduction of the surface of the wax pattern from which it is made. Excessive roughness or irregularity on the outer surface of casting that necessitate additional finishing and polishing. So what are the causes of the surface roughness? The causes of the surface roughness, it could be number one, too rapid heating. So rapid heating of the investment, it can result in cracks and fins on the casting. So it can be avoided by heating the ring to 700 degree Celsius over at least 1 hour. That would prevent the cracking. Second is the water powder ratio. A higher water to powder ratio and large particle size of investment that can lead to rougher casting. So prolonged heating can cause the mold cavity to disintegrate. So it can be avoided by complete the casting process as soon as the ring is heated and ready. Other is overheating the gold alloy can lead to disintegration of the investing material. Other causes of the surface roughness, that could be excessive wetting agent or slabby contamination that may form film on the pattern surface, and that can be reproduced on the casting surface. Using casting pressure that are too high or low can result in surface roughness. Other are the surface irregularities. They are the nodules that could be seen on the surface. So the presence of small nodules on the casting caused by air bubbles that become attached to the pattern during or after the investing procedure, that can cause a challenge in the dental casting. So what are the causes of small nodules or air bubbles? So during the investment, air bubbles can become trapped on the surface of the wax pattern or within the investment material. So proper mixing of investment should be done. So the best and most effective method is to use vacuum investing. So vacuum investing technique, it is the best method to avoid air bubbles. So this technique will help to remove the air from the investment mix. Other are the manual method. One can use mechanical mixer with vibration, or consider using the wetting agent to prevent the collection of the air bubbles on the pattern surface. So apply wetting agent in very thin layers on the wax pattern. Air drying the wetting agent. Allow the wetting agent to air dry, as excess liquid can dilute the investment material that can lead to surface irregularities on the casting. The presence of water film on the surface of the wax pattern, it can during the casting process can lead to surface irregulation. So as we know that the water, the wax, it is repellent to water. So if the investment material becomes separated from the wax pattern in some way, water can form irregular films on the surface of the wax. So that would appear as ridges or veins on the wax pattern. So suppose if the wax pattern it is moved or vibrated after the investment is applied, even it can lead to formation of water films on the wax surface. So use the wetting agents, control the liquid powder ratio. Too high liquid powder ratio can contribute to occurrence of surface irregularities. So use a wetting agent, use correct liquid powder ratio. Others are the fins. So fins can occur when the investment material flakes or break off and enters the mold cavity. So entry of water or steam into the mold cavity can lead to disintegration of the investment material, resulting in formation of fins. So the water entering the mold may contain salts, which can be left behind as the water evaporates. So that can cause salt deposit on the casting surface. So prevention is by gradual heating. It is necessary to prevent the formation of fins. Rapid heating can cause the investment material to disintegrate and release particles into the mold. Other could be water and steam control. Use of proper investment mixing. So ensure that the investment material is mixed properly with the correct water to liquid powder ratio, so that a more stable investment is produced that is less prone to flaking. Underheating. Insufficient heating during the casting procedure that can lead to defect in the final casting. Proper heating ensures the metal alloy reaches its optimal melting point for a successful casting. Incomplete elimination of wax residues. The residues of wax pattern that remains within the mold cavity, they can lead to voids and imperfections in the casting. Voids from the gases, the voids from the gas bubbles within the investment can result defect in the casting. The casting may be covered with carbon coating that can lead to incomplete wax elimination if the mold is heated too low at temperature. So how can you prevent that? Ensure proper uniform heating, allow all the traces of wax pattern to eliminate all the traces of the wax pattern that avoid voids and imperfections. Avoid overheating or using low temperature when heating the mold to prevent carbon coating on the casting surface. Prolonged heating, product of decomposition may be seen like sulfur compounds that may contaminate the alloy, affecting the surface texture. Now let us discuss the various investment materials. One can use gypsum bonded, phosphate bonded, or ethyl silicate material. The gypsum it shrinks at temperature between 200 and 400 degrees Celsius. So it slightly expands between 400 and 700 degrees Celsius, and then it undergoes significant shrinkage. So in order to compensate for this shrinkage, we add silica that act as a refractory component. So by adding silica, the shrinkage can be reduced or even turn into expansion. So there could be normal setting expansion, hygroscopic expansion, or thermal expansion. Other is the phosphate bonded investment, mainly used for metal requiring high melting point. Type 1, it is used for inlay grounds. Type 2 for partial denture and removable prosthesis. The refractory material here is silica in the form of cristobalite or quartz. The binder is magnesium oxide and monoammonium phosphate. Other is the third investment is the ethyl silicate investment. So let us discuss coming back to the porosities that we were discussing. The solid porosities include the localized shrinkage porosity. So remember, the localized shrinkage porosity, it generally occurs near the sprue casting junction. So that occurs due to the uneven cooling. Or solidification of molten metal as it enters the mold. So when the molten metal, it will enter the mold through the sprue, it begins to cool and solidify, but the rate of cooling may not be uniform through the casting. So the casting near the sprue junction tends to cool more slowly. That leads to localized shrinkage porosity. So that is why it generally occurs near sprue casting junction. So what is the solution to this localized shrinkage porosity? So adjust the design of the sprue and the gating system to promote more even metal flow and cooling. Make sure that sprue is adequately sized to allow for smooth and balanced flow of the molten metal into the mold. So one can do is attach the sprue to the thickest portion of the wax pattern. The sprue, as we know, this sprue is a channel or passes through which molten metal would flow into this mold cavity. So to reduce the risk of localized shrinkage porosity, it is advised to attach sprue to the thickest portion of the wax pattern. So the thickest portion of pattern would have greatest volume, and one can get benefit from additional molten metal supplied by the sprue during solidification. As the molten metal, it cools and solidifies, it contracts or shrinks in volume. So by attaching the sprue to the thickest portion of pattern, you ensure that there is ample amount of metal available to compensate for this volume contraction. Other thing that you can do is flaring the sprue at point of attachment. So flaring means expanding the diameter of sprue. Where it connects to the wax pattern. So flaring will help to distribute the flow of metal into the mold cavity. So that will reduce the turbulence and promoting a smooth metal flow. So this technique helps to prevent the localized shrinkage porosity by ensuring that the metal reaches all area of mold cavity, including those near the sprue attachment. Flaring the sprue at the point of attachment, typically at the 45-degree angle, it is the key technique in dental casting. So the turbulence that can lead to defect in casting. So by flaring the sprue, you reduce turbulence. So turbulence, what do you mean by turbulence? It is the irregular motion of the fluid characterized by swirling currents. So this turbulence, it can occur when the flow of metal it is disrupted, so causing it to move in a non-uniform and unpredictable manner. So the primary purpose of the flaring is to ensure the molten metal reaches all the area of mold cavity uniformly. It is especially important near the sprue attachment, where the localized shrinkage porosity is more likely to occur. Other thing that you can do is placing a reservoir. Placing a reservoir just close to the wax pattern. So this is the reservoir which has been placed. So reservoir, what is reservoir? It is a component of the sprue system that holds extra molten metal that compensate for the shrinkage during solidification. So placing the reservoir close to the wax pattern, especially near the area that is prone to shrinkage, would ensure a continuous supply of molten metal to those regions. So this reservoir will act as a buffer, providing the additional metal to counteract the shrinkage that occurs during solidification, and that is why it reduces the risk of porosity. The next porosity is the suck back porosity. Before coming to that, one should know what is hot spot. The hot spot typically refer to localized area within casting or weld where the temperature is higher than the surrounding region. That is why it is known as hot spot. So here the temperature is higher than as compared to the surrounding regions. So these hot spots can occur due to the various reasons like uneven heating, molten metal flow. So these hotspots can cause problems like that can lead to issues like rapid solidification, incomplete fusions, etc. Now let us discuss the suckback porosity. The suckback porosity, the hotspot will cause these suckback porosity. So it occurs when a portion of the molten metal within the casting solidify before it can completely fill a void or fill a cavity in the mold. As the molten metal it solidifies, it contracts and create a void within the casting. So when the casting cools, so this cavity remains as porosity defect. So the suckback porosity refers to phenomenon of the metal being drawn back into the solidified portion as it cools. Now, what is the difference between the localized and the suckback porosity? The suckback porosity occurs when the portion of the molten metal within the casting solidify before it can complete fill a void in the mold. So as this metal solidify, it contracts and creates a cavity or void within the casting. So the mechanism suckback refer to phenomenon of the molten metal being drawn back into the solidified portion as it cools. So that contraction results in formation of void. So suckback typically creates a well-defined and spherical or oval-shaped voids. The suckback can affect the structural integrity of the casting, especially if the voids are large, whereas the localized shrinkage porosity, it is associated with the localized area of porosity within the casting due to uneven cooling or solidification rates during the casting procedure. Unlike the suckback porosity, the localized shrinkage porosity does not involve the metal being drawn back, which cause certain areas of casting to solidify more slowly, leaving voids. So the localized shrinkage porosity, it can take various forms like irregular voids, pinholes or small cavities within casting. So the suckback porosity, it is defined by well-defined voids caused by metal contraction, whereas the localized shrinkage porosity that results from uneven cooling, and it appears as irregular voids within the casting. Now, what is the cause of the hot spot The first of all, geometry and the design. The design of the dental restoration, including the features like line angle and sharp angle, it can affect the solidification behavior. So the sharp, remember the sharp the sharp angular features tends to cool more slowly than the rounded ones. So the design of dental restoration, features like line angles and sharp corners, it can affect the solidification behavior. Sharp angular features tends to cool more slowly than the rounded ones. That causes hot spots, leading to hot spot where the metal solidify last. So uneven cooling within the mold, it can contribute to hot spot. If the certain areas of mold that have better heat dissipation than others, then they may cool more quickly. So that can lead to the suckback porosity. The flow of metal can affect solidification. If metal flow is turbulent or not well controlled, it can result in uneven cooling and hot spots. So to avoid hot spots in dental casting, ensure the design of restoration, optimize the sprue gating system, control the casting temperature, and ensure even cooling. Additionally, rounding the line angles in the design, it can help to promote more uniform solidification. So that can even reduce the risk of hot spot. The other is the microporosity. The microporosity and the solidification shrinkage, they are the common casting defect that occurs during cooling and solidification phase. So these defects can be exacerbated by the rapid solidification and low mold casting pressure. The microporosity, that refers to presence of tiny closely spaced voids within the casting structure. So these voids may be too small to see with the naked eyes, but it may weaken the casting and compromise its structural integrity. The solidification shrinkage occurs when the molten metal from the liquid to solid state and it contracts in volume. So this volume reduction can lead to voids or the shrinkage cavity within the casting. Other is the pinhole and gas inclusion porosities. That can be due to entrapment of the gas during solidification. The pinhole porosity, that is characterized by small size spherical voids in the casting that results from the gas dissolved in the molten metal that is expelled during the solidification. What are the most common gases? Like oxygen, hydrogen. So these can absorb water. So these are the gases. Other is the gas inclusion porosity, that is characterized by large spherical voids in the casting compared to the pinhole. So compared to pinhole, the gas inclusion, they are large spherical voids. So that is caused by gases that are mechanically trapped by molten metal in the mold, or using the improper use of the flame zone. So both these type of porosity, it can weaken the casting and affect their quality. Other is the subsurface porosity. So that could be due to the nucleation of the solid grains and gas bubbles at the first moment that the alloy freezes at the mold walls. So the nucleation refers to the initial formation of the solid grains within the molten metals as it begins to solidify. So the presence of nucleation site, it will affect the subsequent growth of the solid grains. So that in case where the nucleation is not well controlled, that could lead to formation of small voids or the pores within the casting. That contributes to the subsurface porosity. Gas bubbles like air or other volatile gases that can be entrapped. So that can even result in subsurface porosity if the bubbles, they don't have a path to escape, or using a short thick sprue. The design of sprue, that is the channel through which molten metal flows into the mold, it can impact the casting procedure. A short and thick sprue may not allow for adequate degassing or escape of the entrapped gases. So that can lead to gas related subsurface porosity. If the mold temperature is too high, that can allow more time for entrapment and immobilization of gas bubbles. That can even lead to subsurface porosity. Other is the back pressure porosity. So when the air bubbles, they become entrapped within the casting, particularly on the inner surface. So these air voids can result as concave depression on the casting surface. So the main cause includes the inability of air in the mold to escape through the investment pores, or the pressure gradients pushing the air pockets toward the end of the investment. So it is mostly found in a pocket at cavity surface of the dental crowns. In some cases, it can occur on the outer surface of the casting when the casting or the mold temperature is too high. So in order to eliminate air porosities, use proper burnout, maintain adequate mold casting temperature, apply sufficient casting pressure, and optimizing the liquid to powder ratio. Other important thing is the thickness of the investment between the tip of pattern and end of ring. It should not be greater than 6 mm. So this chart is very important for your exam point of view. So it remember, for your exam point of view, if the sprue thickness is increased, what will be the effect on the localized shrinkage porosity, subsurface porosity, or the micro porosity? The localized shrinkage porosity would be reduced. If the sprue length is increased, the subsurface porosity would reduce. Increasing the melt temperature would reduce the localized shrinkage porosity. Increasing the mold temperature would reduce the localized shrinkage and micro porosity. So many questions can be asked based on this chart. Remember that. The other is the incomplete casting. That means partial incomplete casting or perhaps no casting at all is found. The cause is the molten metal that has been prevented in some manner from completely filling the mold. So the reason could be insufficient venting of the mold. The venting in mold refers to the provision of the pathway or channels for the gases such as air or volatile substance to escape as the molten metal flow in the mold cavity. So when the mold lacks proper venting, the gases that are present within the mold or released during the casting procedure may get trapped in the casting material. So these trapped gases will prevent the molten metal uh, from properly filling all the parts of the mold that would lead to incomplete casting. The other is the high viscosity of the fused metal. Viscosity, it is the measure of material resistance to flow. So when the molten metal, it has high viscosity, that means it will flow less easily. So it will be having difficulty to reach all the parts of mold, especially the narrow section. So the high viscosity molten metal may solidify too quickly before it can fully fill the mold, that results in incomplete casting. So the choice of casting material and temperature, it can influence its viscosity. So metals with high melting point tends to have higher viscosity. So proper casting temperature control and selection of casting alloys with suitable viscosity for specific casting application, they are important to prevent the incomplete casting.